Hello and welcome to another video of integration techniques. So we're gonna start with the substitution technique, and then before I give you some examples, I would like to give you an idea on where this comes from, where the substitution technique comes from, because it's important to always recall that integration is sort of like the opposite operation of differentiation. So I know you are eager to see the example, but let's go through this before we actually do some examples. So as you can see here, I have the substitution technique is based on the chain rule for differentiation, and that was it. And remember what I mentioned in the introduction, it was important to see to actually understand the differentiation techniques before we actually go into integration. So for differentiation in the chain rule, the substitution will come from there. So let's see why is that. Now if you recall the one theorem from your calculus class, the chain rule is a chain rule about composition of functions. When you compose two functions here, f composed with g, you take the derivative of that is the derivative of the function f evaluated at g times g prime of x. And you might have seen this, some books say like is the derivative of the outer times the derivative of the inner. And all these words that are here in the theorem is basically to make sure that that derivative will exist. So g has to be differentiable at x, and f has to be differentiable at g of x, because you want this right hand side here to exist. So that's basically the chain rule, is the derivative of the outer evaluated at the inner function g of x times the derivative of the inner function, which is g of x in this case. So this is the theorem on which the substitution method is based on. Now we're gonna assume that the chain rule is true for some open interval, so everything I'm gonna do is actually gonna make sense. So I can write down the derivative of f composed with g as d dx of f composed with g evaluated at x, which is by the chain rule is equal to this right hand side here. Now, if we look at this equation that we have here, and I'm going to just do an anti-differentiation there. So I'm going to just write down the symbol of integration on both sides here of that equation. So what I get is this, is the integral of d dx of f composed with g is equal to this integral here, which, you remember, this part and this part are the ones that come from the chain rule of differentiation. Now, one thing you should remember also is something that I said many times, is differentiation and integration are one opposite of the other. So if I differentiate and I integrate, then I'm going to get exactly the same thing. So I'm going to get the following. Once I call this f prime f, just to simplify a little bit the notation, instead of calling it f prime, I'm going to call it f, just to simplify notation. So what I get is this, that f composed with g is f, capital F, which is I call f prime, is just notation f prime of g of x times g of x prime. So this right hand side that you see here is actually that substitution rule. You have an inner function g of x, which you're gonna call u, and the derivative is outside. So this will make more sense when we go into the example. So this is just an introduction on where this substitution rule comes from. And on the right hand side, I have this f composed with a g evaluated at x. So f composed with g evaluated at x is the same as f evaluated at g of x. That's just the definition of the composition. And on the right hand side, I had the same I had before. Now, if I'm actually, this is where the substitution comes into place. If I call g of x, this one that is inside here, the integral, if I call it u, then the u, which is the derivative of that, will be the derivative of the function g times the x. So we're using differentials here. So if you see that, then the g of x will become u, and this whole part here, g prime of x dx, will become the du. And of course, I'm going to replace the g of x here on the right hand side. I'm going to replace it by u. As you can see here, this is the substitution. So all this technique of substitution comes from the chain rule of differentiation. So that's basically the idea I want you to take from here, that substitution rule comes from the chain rule of differentiation. So before I actually give you an example, and I know you are eager to see the example, let's hold that for a second, because I want to discuss first how to apply the substitution rule, because it's going to be important. It's going to help you choose wisely what the variable u is, what g of x will be for your variable u. So when you choose u to be an expression, that expression has to be inside the integral. Usually what happens is that u is usually an expression that is under the square root or some root, or is the denominator from fraction, or is the argument of some function. That usually is the case for that choice of u. So that's how you choose your u. Now, that when I say usually, it means that sometimes that doesn't work. Sometimes it's not in this kind of matter, but most of the time, for most of the examples that you will see in the textbooks, it will be like that. It will be some kind of something that is inside some square root, the argument of some function, something like that. Now, once you make that choice of u, what you're going to do after that is you're going to compute the derivative of that. That's why you need to know what the rules of differentiation are, so you'll be able to find this second part. The u will be the derivative, which is whatever the derivative is, and you multiply by dx. Don't forget to put the dx here. I have seen many people do that and they forget to put the dx at the end. That's also important because notation is also important here. Now, once you take the derivative, u has to be an expression inside the integral, and the u, once you take the derivative, should also appear inside the integral. That should give you an idea that you chose the right u. If you chose the right u, the derivative should also be inside the integral. And once you make the substitution, and this is also a very important part, the third part is when you substitute u in du, this new integral that you get, which is all in terms of u, should be easier than the original. The purpose of the substitution rule is to make things easier. So if it doesn't get easier, that means then you made the wrong choice for u. So you have to choose another u. And we will see examples in a second. And so that's basically the idea for the substitution rule. Now, I will go over examples and you will see how this works exactly. So, but I'm going to refer to this technique on how to choose the u, how you have to compute the derivative, and how once you make the substitution, the new integral should be easier. So I'm going to go to the blackboard and I'm going to show you an example where I'm going to apply these techniques. So I'm here in the blackboard, and so I have this example here. So I'm going to call this example number 1, and I'm going to call it perfect substitution. And the reason I'm going to call it like that is going to come in a second. So because the substitution here is going to work perfectly. Sometimes it doesn't work like that. We have to fix something, but in this case it's going to work very well. So let's say we want to find the antiderivative of 2x times x squared plus 1 to the 5th dx. Now, if you look at this expression that is here, you could have the idea, for example, so we could expand this and integrate using the power rule, which is something that you don't want to do in general, because this power could be large, and if this power is large, then you're gonna have a really big expression. I'm not gonna do it like that. The purpose of this example is to do a substitution, but let's just look at what will happen if you actually attempt to do this in the old-fashioned way. So the old-fashioned way will be, I'm gonna expand x squared plus 5 to the 5th. So multiply x squared plus 1 5 times and multiply by 2x. If you do that, you're gonna get this expression that is here, which is a very long expression. Now this, of course, you can integrate it because the integral distributes with respect to a sum. So you can integrate x to the 11, x to the 9, x to the 7, and so on, which will be easy to integrate because it's power rule. So for example, the integral of x to the 11 will be x to the 12 divided by 12. That's the power rule of integration. But you don't want to do that. And the reason you don't want to do that is because, for example, if I change this power, for example, to the 12, then this expression will be truly too long to just do it like that. So best way to do this is use a substitution. So let's go ahead and do that. So again, this is not a good idea to do it that way. So we're going to use a substitution. So what I mentioned earlier in the video is the first thing you're going to do is you're going to choose u that is an expression that is inside the integral. And usually what works is something that is under the square root, denominator, or the argument of a function. Now, in this case, if you look at the integral we want to do, the u here is something that is inside the integral. So it has to be something here and is an inside function. So what will I choose here? It's something that is inside of some other function. I have the fifth power here. Something that is inside is this one. So let's try that out. Let's try u equals to x squared plus 1. And that's an expression that is inside the integral. So something that is there inside, and is the inside of is the argument of the fifth power in this case. Now, once you make the choice of u, whatever that is in here, you want to find the derivative of that. That's the technique. So then we're going to compute du, which is the derivative of that function. In this case, it's x squared plus 1. You're going to simplify, and the u has to be also inside the integral. So let's compute the derivative from here. So what is the u in this case? So du will be the derivative of x squared plus 1. And I'm going to apply the power rule of differentiation. So it's going to be 2x. And of course, the derivative of 1 will be 0. And because I'm done, I'm going to multiply by dx. Remember, it's important you add that. Now, this expression that is here should be inside the integral. And let's go back and see if it is. So, yes, 2x dx is also inside the integral. That tells you that you sort of make the right choice of u. So if you choose u, which is in this case x squared plus 1, the du should also appear, this is the u, and the du should also appear inside the integral. So that's the second part of the thing. The third part is you're going to make the substitution of u and du inside your integral to get a new integral. So what do I mean by that? So we had this integral, which is 2x x squared plus 1, that was plus 1, to the fifth dx. I'm going to organize it in this fashion so you can see exactly how the substitution rule is going to work. So I'm going to say this is the same as x squared plus 1 to the fifth times 2x dx. This expression that is here is exactly the same as the expression I have over here. I just changed the order of multiplication. Now, the reason I put it like that is because now I'm going to make the substitution. If you remember, what was our u? U was this expression here, x squared plus 1. That's my u. And this guy here that is 2x dx, that is my du. And if you scroll, let me scroll back here and show you. So du is 2x dx, and u is x squared plus 1. That's where I make the substitution. So now if you go back here, and then I'm going to write down everything in terms of u. So this is going to be the integral. Instead of x squared plus 1, I'm going to say u. So I'm going to say u to the fifth. And then this whole thing, 2x dx, is just the du. Now, one thing that also tells you that you made the right choice for the substitution is that this integral should be easier than the original. The original, I had to do an expansion and do all that, but this guy here is just a power. And we know how to do, or how to compute powers, the integral of powers, the antiderivative, which is only you take u to the exponent, which in this case is 5, plus 1 over 5 plus 1 plus the constant c. In this particular case, this guy here is the value of n, so which is this n over here, and which is this n over there. So that is the power rule for integral. If I simplify that, I'm going to get u to the 6th power divided by 6, and then plus the constant of integration. Of course, you don't want to actually now just leave it like this. You have to go back to the variable x, which is the original question. The original question is in terms of x. So what we're going to do is I'm going to replace back now what this variable u is. Now, if we scroll all the way back here, let me scroll all the way back. What was u? U is x squared plus 1. So I'm going to replace the u by x squared plus 1 to get my answer in terms of the variable x. So in this case, then this is going to give me x squared plus 1 to the 6 divided by 6 plus c, and this is going to be my final answer. So
The idea here was that we use a substitution and we make things easier. So why? Because we had a power basically here. So we got the answer here. You can check that this is actually correct by taking the derivative of this expression that is here, and we should get back 2x, x squared plus 1 to the third power, which is going to be the case here. So what I'm going to do is I'm going to finish the video here. This is the first example, and this is a perfect substitution is because I didn't have to do any fixing. So everything appeared exactly as it was supposed to be. U was here, the du was there. That's not always the case. Sometimes the du doesn't appear exactly as you want it to be there. So that's what we call not perfect substitution. But this is a perfect substitution. And in the next example, I'm going to give you another case where we actually also have a perfect substitution. So I will stop the video now and I will see you in the next video. Thank you very much for watching.